interesting Casper was, and Danny was talking about trying to catch up and asking about how does our chain fit into the Casper research. And so I was talking a little bit about that. Now, one of the things that I was pointing out is that the justification pointers, which play a large role in, or the justification structures in the message flow in Vlad's correct by construction version, were actually originally suggested by me as a part of an analysis of the needs of the Casper protocol, and it goes back to a different kind of game theory. So I mentioned to Danny that there are, in fact, 3 major forms of game theory. There's the kind of familiar von Neumann-Nash style games, but there are at least 2 others. One of which is Conway's games in the branch of research where called the surreal sometimes called the surreal numbers. Conway captured it in a lovely book called On Games and Numbers. And that's distinct from Conway's work on the game of life. And then there's another branch of game theory called the Abramsky-Hyland-Ong games. And Hyland and Ong use the notion of justification pointers to essentially capture the notion of single-threadedness. And I've been using this in protocol development and protocol analysis since around 2009. In 2010, you can go and see the special K repo, which is the first version of the content distribution network that sits underneath our chain, utilizes justification pointers as a part of the message format and message framing data structures. So we've already tested this idea of using justification pointers at scale fairly significantly. And Vlad took this idea and ran with it. So this is one of the ways in which our chain work has been informing Casper. Another way in which, and it's kind of important to understand that the Abramsky game theory gives rise to closure operators as ways of playing strategies against one another. And this connects fairly directly to the notion of a trace. And I have been arguing rather consistently that the notion of trace in the categorical sense is the appropriate equational characterization of consensus. And this is, in fact, something that Vlad and I were discussing last week. So that's another way in which these things connect. And then finally, it's quite interesting that you mentioned this, Danny, because just last night I was working, and this is part of my update, I was working on a paper regarding the consensus algorithms. So I was working on sort of talking about it from the perspective of constitutional guarantees of liberty. Because I think that there's a deep connection. I sort of think of the Constitution. I think it was Stuart Brand who coined this phrase about the Constitution framers. The Constitution was witty code by witty programmers, and I think that's quite true. One of the rights that they felt was important and actually stands as the First Amendment to the Constitution is the freedom of assembly or the right to peaceable assembly. The consensus algorithms that come to us from this sort of proof of work and Casper and others, these decentralized consensus algorithms that favor availability over consistency, they provide some of the things that are necessary for free assembly. And I don't just mean free assembly of human agents or even organizational agents made of human agents. I also mean the freedom of assembly of computational agents like smart contracts. I just want to make sure that this is making sense, Danny. Does this make sense so far?
Yeah. I'm just taking it in.
Cool. Sweet. So in particular, one of at the foundation of consensus, at the foundation of the freedom of assembly, the way in which the consensus algorithms provide a kind of support for freedom of assembly, is the ability for agents in the digital space to rendezvous. So here's what I mean by that. In one of the great advantages of the digital space is that agents can connect anytime, anywhere, right? There's a kind of virtualization of creating connections that overcomes geography and the clock.
Right.
Yeah, so that's kind of cool and it's great, but it also means that we have to have means to coordinate with each other. The connect anywhere, anytime becomes a form of isolation if we can't coordinate, rather than a form of connection. So agents need to be able to say, let's meet there then, and have a common understanding of what there and then are. And if you think about it, the notion of Bitcoin addresses provides a very, very basic building block for a notion of there. And
is it not a notion of who or whom?
No, it isn't actually a notion of whom. It's decidedly not a notion of whom. That's kind of the point. It's about anonymity. You don't know who
Right.
Address. But it's a good question.
But they do represent entities.
Again, you don't know what kind of entity
right.
Rather, it's a location that entities can utilize to communicate.
Okay, I get that.
In other words, they become rendezvous points. So that gives you the awareness.
Okay.
And the same is true of Ethereum addresses. More intriguingly, the same is true of URLs and URIs. They give a kind of awareness to resources, and all of these systems have this basic feature because they're designed for the coordination and communication of agents. So they have to provide a kind of awareness. And recently, Vitalik did this funny thing where he held up a recent hash, block hash, as proof of life, and this gives you the sense in which the blockchain is giving you a wimness, right? So the steady march of blocks gives you a notion of win, and so the consensus algorithms, together with some basic infrastructure, such as blocks or other kinds of things like that, provide a where and when for agents to assemble, because they can now coordinate their getting together, and that's really that's fundamental to the right to peaceable assembly. Additionally, there's another level to this, and it shows how some of the constitutional rights fit together. The next level has to do with the ability to signal each other. So agents have to be able to signal each other in order to effectively coordinate. So they could get together in a room, but if they can't talk to each other, then it's not a very effective assembly.
So is that free speech?
That's exactly free speech. That's right. So freedom of assembly and freedom of speech interact with each other. They're intertwined or interdependent on each other. And so if you look at the blockchain, this is the Bitcoin blockchain. It provides signaling via numbers, via economics, and that's a robust and nuanced form of signaling that we understand, right? It's it's the basis of using market mechanics to drive behavior. So that's one form. And then the Ethereum blockchain suggests that we could use programs to signal each other. So this is the improvement, which is smart contracts, right? And so this is also, and I argue that this is one of the reasons why there's such enormous economic speculation around these networks which don't actually scale. So it's because people understand that the freedom of speech, the signaling mechanism in the Bitcoin blockchain is such a crucial part of a re-envisioning of a society that is more decentralized, and the ability to use programs as opposed to just numbers to signal represents at least the possibility to coordinate even more effectively. And so I think that's why there's such huge and enormous economic speculation around these networks and platforms. But it turns out that there's yet another level, and this other level, and gets right to the answer to your question, Danny. So the next level up is that if agents are forced to assemble in a top-down fashion, or they're forced to assemble in a way in which their view of events is organized in a global serial order, then the assemblies will not be efficient. They won't be effective enough to work at global scale. So I want to, at least in the way I was writing the white paper, and I think this is the kind of metaphor that I've been utilizing. If you think about, a bunch of leaves on a tree, and then a bunch of trees in a forest, and then a bunch of forests on a planet, right? That kind of participation is what all of those agents are participating in the maintenance of the very air that we breathe. So that system of exchange, carbon dioxide and oxygen and other gases, is enormously complex, astoundingly complex, and yet it's also astoundingly robust. It has endured just really, really profound changes over literally millions of years. So
by the top-down organization, you mean how the blockchains that are like how Ethereum and Bitcoin are currently implemented?
Well, I'm getting the short answer is yes, but I'm getting to a more subtle answer.
Gotcha.
So again, if we think of these agents as programs, computer programs, smart contracts, then if the model of programming is top down, has no way to talk about autonomous, independent execution, then you can't get to this scale that would be robust enough to maintain the air we breathe. But certainly not there. But also not even to the scale of financial networks. So one of the points that I try to make again and again and again is the reason financial networks scale is that most transactions are autonomous. They are independent. And so if you need a global serial order, then you won't get to the scale of the existing financial networks. And if you need a top-down approach to the coordination of agents, then you won't get to be able to the kinds of efficiencies necessary to support things at scale. So what we're saying is that freedom of assembly demands things that we see in the consensus algorithms, but it also demands other things. It demands things of the model of programs that we use both for agents to signal each other, but also, and that model turns out to be equally applicable to the agents themselves when the agents are computational agents. So that's a kind of subtle idea. What we're saying is that programs use programs to signal. And that turns out not to be surprising. It's already happening. If you think about programs that ride at the HTTP level, they use programs at the both at the HTTP level and the TCP level, both to unpackage and package network communication frames, right, as well as to coordinate their behavior. So this is actually very standard in network programming. It's understood by people who program in networks, and it's not surprising that it should show up again here in the blockchain space. So what we're saying is another way of saying this has to do with what Vlad and I have been talking about with respect to applying his algorithm to a wider range of things than just a bit or a notion of a blockchain. So what we've been talking about is applying it to being able to write it down in a way that it is general enough that it applies to arbitrary computational mechanisms. So so you could think about this, right? What would you, if you could replicate any kind of computer, what kind of computer would be useful to replicate? So at the low end of this, you could say, well, let's replicate regular expressions. Regular expressions are very useful. They get a lot of work done. It's hard to program on most operating systems today if you don't know regular expressions. So that's, but it's a very limited form of a notion of computation. And you could kind of go through each of the different notions of computation and see, or programming model is another way of saying it, and say, well, which of these has this ability to be efficient in the way that we were talking about? And it turns out that if they're basically just, a handful of characteristics they can utilize to select amongst the different kind of programming models at their core. And that's what I did a long time ago, was to kind of analyze all of the theoretical approaches to programming models, which then gave rise to different families of programming languages, and to characterize them in terms of a fairly robust and distinguishing set of characteristics. So the characteristics there are four that cover a huge space. One is completeness. So regular expressions is not complete. It's not computationally complete. Right? You can't write down any program that you might write, say, in Scala in regular expressions. You can write down any regular expression in Scala, but not the other way around. So completeness, and this idea of Turing completeness is one of the things that Ethereum picked up. Another one is, does the model itself have a notion of resource? Can we count things like computational steps or use of storage? Because once you have completeness, then you need to be able to throttle computations to avoid denial of service attacks. So it turns out that there are models of computation that don't have good notions of resource that are still Turing complete. A really good example is the lambda calculus. The plain vanilla lambda calculus is terrible when it comes to the copying of values. So its notion of data storage resources is very, very slippery. And that's why there wasn't a lot of complexity theory carried out on the lambda calculus in the early days, until Girard came along with linear logic, but that's a different story. You can also ask, and this gets to this idea of efficiency. Does the notion, the programming model, come with a notion of composition, right? So we thought about, leaves composing into trees and trees composing into forests, and forests composing into ecosystems that maintain the air we breathe. So that idea we understand as engineers. We want to be able to write programs and then write larger programs that assemble those programs, freely assemble those programs together to get a larger job done, and then write even larger programs that freely assemble those programs into something that gets another job done. So that's the notion of composition. And not every model of computation, not every programming model has a good notion of composition. A really good example, one that's close to home here, is Turing Machines. When Alan Turing first considered the Turing machine, he didn't think about a system in which you could whack two Turing machines together and get a third Turing machine, to compose two Turing machines into a larger Turing machine, even though he informally used that idea in his famous halting argument. So those models, those characteristics of programming models are actually enlightening, because they allow us to distinguish amongst different kinds of programming models and say which of them we might want to replicate for the kind of system we're imagining when we imagine a blockchain-based computer. And the fourth characteristic takes this even further. The fourth characteristic is concurrency. And this gets right to the heart of the conversation that we had when we talked about efficient assembly, the ability for the agents that are assembling to act independently, autonomously, as well as in a coordinated fashion. So they have both the capacity to engage in a coordinated way and the capacity to engage independently, to act on their own. And this is really at the heart of liberty, right? This is really, really one of the things that we understand when we understand liberty. And it turns out that the model of computation that's used by Ethereum doesn't have this at its core. It's really more of a top-down form.
Right.
Yeah. But the model in our chain does have this. And in fact, what you can do is you can go and do an analysis of all the models of computation. And you'll find that until the mobile process calculi came into focus in concurrency research, there was a big gaping hole for models of computation that had all four properties. And it's only currently, eventually we expect that there will be other models of computation that have all four properties. But at the current time, and this has been the case since 1989, when the mobile process calculi were discovered, there hasn't been another candidate that has all four properties. Now, the mobile process calculi include things like the pi calculus and the blue calculus and the ambient calculus and the join calculus. And you can go and do the same kind of analysis on each of these candidates that I just did across all the computational models. And at the end of the day, there turns out that there's one version or one variation of the mobile process calculi that has enough characteristics to make it be practical to satisfy the kinds of things that we really do with programs when we talk about programming at scale. And so our current best guess is the row calculus, because not only does it have all these other features, these 4 characteristics. But it also ties together meta programming, which is something that every programmer who works at scale knows and uses on a regular basis. So using programs to write programs, right? So we do this every time we use an editor, right? A text editor. We're literally using a program to write programs. But we also do it in a more direct fashion when we use templates or macros or reflection, as we find it in Java or C#. So the meta programming is what enables us to use computers to help us write computer programs, or to use programs to help us write computer programs. And that's necessary to code at scale. So now, wrapping it all up, this is a super long-winded answer.
Great answer.
Wrapping it all up, our chain is using models of computation that have informed the basic protocols of Casper, down to the very technical details of justifications and justification pointers. But we're also utilizing models of computation that we believe are sort of naturally selected, and pun definitely intended, for the kinds of applications that we intend for the blockchain. So that's how it fits together, at least in my tiny mind.
Right, but the inadequacies of the computational model of, say, Ethereum and Bitcoin that are bettered in the R chain is the Ethereum Foundation and those guys, are they looking into moving in that direction, or are they these two projects kind of moving in parallel right now and informing each other, but Ethereum's not looking to switch the computational model?
So Ethereum is being forced to change the model slowly and surely. And there's no way around it if you're going to go at scale. And,
right.
But the problem is that they haven't sort of got it in their bones that it's a fundamental shift, and it's better to shift the computational model. And I learned this the hard way. I kind of did the very same kind of thing that Ethereum did back in the 80s. I saw that computation. So first of all, I was working at a research lab called MCC. And we all, at that time, predicted the commercialization of the internet. You know, back in those days, a lot of people still called it the DARPA net, right? So that's how old. So we predicted the commercialization of the internet. And one of the things that I saw was the need for concurrency, and so that I went and looked at like practical applications, practical models. And the very first thing I tried was concurrency in a scheme-like setting, so the programming language scheme, where you derived your notion of concurrency from instantiating multiple versions of the virtual machine. And I saw the limitations of that. I saw that wasn't going to fly. And so the next thing I tried, so then I said, okay, so it has to be more fundamental than at the granularity of the virtual machine. And by the way,
is the internet like the server client model, and that there's tons of different servers on the internet doing different things? Is that the similar kind of concurrency model as the schema virtual machine model?
It's sort of like that, but you could imagine that if the internet composed, right, you had internets made of internets, then it would move more in the direction that I'm talking about.
Okay.
But, yeah. And essentially, that's the kind of thing that the internet wants to be, but hasn't yet become. And this is true because the hardware abstractions also have this kind of weird idea about concurrency, right? The hardware abstractions, like if you look at LLVM, the notion of concurrency really comes down to instantiating different virtual machines, and it's not really composable. And so that's that's a sort of a limitation conceptually that ends up being a limitation when you're trying to realize this on hardware. And that's why you really have to take it in a more fundamental direction if you want it to be to work at production quality. So the next thing I did was I worked with Christine Tomlinson and Mark Scavell and Greg Lavender and a bunch of others on the development of Rosette, which was an actor-based language. So in some sense, the Ethereum model is heavily influenced by actors, but it's not yet an actor model. Rosette was genuinely an actor-based model that was fully reflective, and it was reflective in novel ways. We built out all kinds of commercial applications to test this idea. I personally built an ATM network management system using Rosette and the execution framework called the Extensible Services Switch. We also built data cleaning applications for Kodak and other kinds of we built another data cleaning application for Bellcore. We did suffice it to say, we did a bunch of things at scale to test this model. And one of the things that I found that was problematic with the actor model that I didn't expect to be the case was that the actor model comes with sort of a principal port idea, which is sort of very, very attractive in terms of the way we think about things. So an actor basically has one place where you can contact it, and that's the actor's mailbox. But that turns out not to be how the real world is organized. The real world is organized in terms of multiple ports and coordinating across multiple ports. Even the decision-making processes of human beings are fork-join kinds of things. So rather than a principal port-based approach to concurrency requires a lot of pipe fitting with respect to how things happen in the actual world. And so, after being an actor bigot for over a decade, I finally let go of that, long cherished idea, and fully embraced the mobile process calculi as more practical for working on things, everything ranging from network protocols to workflow systems. I used the mobile process calculi at the heart of Microsoft's BizTalk process orchestration, which was arguably the first internet scale smart contracting system. And that gave rise to a bunch of internet standards, including BPML and BEPL and WS choreography. And I worked on, either worked directly on or worked with members of those standards committees to help inform those standards. All of them derive directly from the mobile process calculus called the pi calculus. And then the rho calculus is can be thought of as a refinement of the pi calculus to add in the meta programming. So that's kind of a little bit more of the history and how all these pieces fit together. So it's very natural because a lot of this information doesn't flow uniformly throughout communities, right? A lot of the work on mobile process calculi, a lot of the work on category theory or on type theory it's still not taught to undergraduates. And so, I mean,
No,
it is
not.
Yeah.
I mean, not much. I
Right.
can say from experience.
Yeah, exactly. So in particular, if you go to high-end European schools, you will get exposure to this pretty readily, pretty handily. If you go to high-end US schools, you're much less likely, but you still might be exposed.
I was not exposed to this at Princeton undergrad computer science, so
exactly. That's kind of my point. So in the U.S., there's a very different flavor of what theoretical computer science, or even computer science in general, means than in Europe.
Right.
Yeah, and so it's very natural for, if you have a revolution, that a computational revolution, a platform revolution, is being fomented by a bunch of 20-somethings, that they never have been exposed to these ideas. And if they've never been exposed to these ideas, they're going to reinvent the wheel. I saw the same thing happening with respect to systems biology and computational biology. It turns out that the mobile process calculi are quite effective in describing biological phenomena. And so I went and sat with a bunch of biologists. I held a position as a visiting scientist at Harvard Systems Biology. I held a position as a visiting scientist at the Trento Systems Biology Lab. And I sat with them, and I was astounded by how amazingly brilliant they were, because they were not only doing biology, but they were reinventing computer science at the same time. They didn't know any better, and so they were doing all these things that their science counterparts had already done. They just needed them.
Wow.
Yeah, and so it's perfectly natural for people in the Ethereum community or the Bitcoin community to be innovative on a lot of fronts, but also regressive in others, to not know about the research that's going on.
Right.
And so that's kind of where we are. And slowly but surely, I believe that these approaches are beginning to inform what we're doing. They're beginning to make an impact. And I think it's necessary, because if we're talking about rebuilding the global financial infrastructure, and which comes along with a reboot of the governance structure, and comes along with a reboot of the application infrastructure that we've come to rely on, all of that is going to require a level of robustness and stability, which we don't see with the existing networks. The DAO bug, the parity bug, all of these we've only survived them because of the good graces of the communities, right? Mm-hmm. So that's important, right? Because it shows that we have communities that are willing to act with goodwill. So that's very important, but it's not enough
because of the early adopter nature of the community. Probably right now.
That's exactly right. That's exactly right. And so the other side of doing the kind of analysis that I've done is that it allows us to do formal verification, to automate a lot of the checks of the correctness of things. So on the one hand, it's more practical because it's more scalable. On the other hand, it's more practical and more scalable because it's more often correct. And so that's the other piece of this, and that level of assurance of correctness is necessary to get to the kind of robustness that these systems have to have at scale.
Okay.
So that's a very long discussion, but that's you were asking about how the two fit together, and
absolutely, and I see it, and I see the informing the Casper research, and I see how you want it to fit together more with the Ethereum roadmap, I suppose. But I guess still, how much is it currently fitting in with the Ethereum, or is it still an open discussion and these guys are kind of like waking up and seeing the potential of what you're talking about, and but not yet informing the roadmap?
Right. So I think that it's not yet Ethereum informing the Ethereum roadmap, except in the ways in which we've talked about informing the development of Casper algorithms. I believe that essentially I came to the conclusion about a year and a half ago that the fastest way to truly inform the Ethereum roadmap was just to go ahead and build a version of this. And once we had a version, then the Ethereum folks would wake up, right? I mean, if we're able to get transaction rates in the tens of thousands, right, which is on par with what we need to compete with Visa network and actual financial networks, then I think people are going to go, well, I could deploy my prototype on a 15 transaction per second network, or I could deploy my prototype on a 40,000 transaction per second network. Which one would I like to do?
Right.
Right. And then people just vote with their feet. And then they can go, well, I could write in a programming model which allows me to commit bugs like the DAO bug, or I can write in a programming model in which the compiler will not even type check those bugs. The bugs will not even pass type checking, because they don't pass type checking, they don't get deployed. Mm-hmm. Right. So I think that's just like vote with your feet time. And then at that point, I think it will have an impact on the Ethereum roadmap.
So is our chain, if it doesn't impact the Ethereum roadmap, is our chain ultimately a competitor? Or an alternate chain that will be public?
It's certainly going to be an alternative chain. My feeling is that we are absolutely helping each other, because the larger goal here is to provide a kind of reboot for a bunch of systems that are essentially too corrupt to fix from within.
Right. And I don't, competitor is the wrong word. I've sat in on enough of these discussions that's not the tone, clearly. More of a collaboration in parallel.
Absolutely. Hey, I noticed that Mike joined. Mike, do you have an update? Or because we're at the top of the hour and I've got to get rolling.
No, just that we had that conversation.
Okay, all right, cool. So I'm gonna hit the road. I've got to go pick up my partner, and so I've actually got to get on the road right now. But
fascinating update. That was I've been curious about that link for probably months now, and you really filled in the gaps. I appreciate it.
Thank you so much for asking the question. And again, please come and talk with us more. We'd love to have your engagement on our chain stuff. There's a lot.
I'm looking. I have some time I'm looking to fill, so I might hit you up outside this conversation.
Fantastic. Actually, Mike can put you directly in touch with Nash Foster, who is running our contracting stuff. So if you want to hit up Mike, so that's is it stay at Pyrofex?
Yes. .net.
Stay at pyrofex.net. Danny.
Pyrofex. How do you spell that?
Pyrofex.
Got it.
Cool. Hey, Greg, can I have a moment of your time later today? It doesn't have to be now if you have to run. Just maybe on the phone. You can text me. I can call you, whatever.
Will do. Absolutely.
All right. Cool, guys. All right, later on.
All right. Thanks, everyone. Bye.